I'm Jeff Grove, and this is Partial Differential Equations.
We consider next the D'Alembert solution. We still refer, of course, to the initial boundary value problem for the wave equation in one dimension. Here, the initial data consists of two parts, since we have two time derivatives. Giving an initial displacement, but also an initial velocity. We must also have boundary conditions. And in this case, we're going to assume both boundary conditions are a displacement of 0, as though we're dealing with a string clamped at the ends. In order to express this solution, we need some notation. In particular, we need to define what we mean by the odd extension of a function. We'll define this in two steps. First, we'll define u bar of x to be u naught of x, where x lies within the usual interval from 0 to L, but minus u naught of minus x when x lies between negative L and 0. You can see we're making an odd function out of some arbitrary function defined on 0 to L. The second step allows us to repeat this function every interval of length 2L. We'll define this function by u star. The solution then to the initial boundary value problem to our one-dimensional wave equation is given by the D'Alembert solution. We'll take the average of this u star, and we're going to not evaluate this at x, but rather at x minus ct. In this way, we're taking our initial data and making the odd extension of that, and then having the odd extension move to the right at a velocity of c. But in addition, we're going to have the same thing moving at the speed c in the other direction. At t equals 0, we just end up with the odd extension. And if we restrict ourselves to the interval from 0 to L, that just gives us the initial data twice multiplied by a half. We just end up with the initial condition. But this does not account for the initial velocity. To deal with that, we require 1 over 2c, the integral from x minus ct to x plus ct of our initial velocity. In this way. Let's see. When t is equal to 0, this integral is 0, so again, we just end up with the initial displacement. In order to show that this satisfies the initial velocity profile, we take the derivative with respect to t. By the chain rule, this first term will give us a factor of minus c. The second term will give us a factor of plus c. When we evaluate at t equals 0, the minus c and the plus c terms will cancel. Down here, we also need to use the chain rule, which will give us a factor of c when evaluating at x plus ct, and a factor of minus c. We'll subtract a negative c. That gives us two terms with a factor of c. When we evaluate it at t equals 0, we'll end up with the initial velocity profile twice over because of the two terms added together but multiplied by a half, and then you just end up with the velocity profile. To check that this satisfies the differential equation, maybe takes a little more room than I'd rather commit to this light board, and so I'll have you work that on your own on paper. Note, in considering the Fourier series solutions that we constructed earlier, consider the cosine of pi nc over Lt times the sine of pi n over Lx. This is a product, and so maybe we should use the product to sum identity. Since it's sine and cosine, we'll have the sine of pi n over Lx minus pi nc over Lt plus the sine of pi n over Lx plus pi nc over Lt. We can simplify this a little bit. In particular, we'll have 1/2. We have a pi n over L on both of these. We'll have x minus ct. So this first term represents a sinusoidal wave moving to the right at a velocity of c. And the second term is simply a sinusoidal wave moving to the left at a velocity of c. In this way, you can see that our previous Fourier series solution is at least plausibly consistent with this D'Alembert solution. I'd next like to turn to the heat equation. The heat equation is a parabolic differential equation of this form. C is the diffusivity constant. This models diffusion problems, not just heat, but diffusion of any number of different things. It could be light, it could be neutrons at a critical mass, it could be any number of things diffusing. Now, because we have only one time derivative, we only get one initial condition. We will, of course, get to boundary conditions. Left and right boundary functions. These are not the only possible initial boundary conditions.
To this point, we've specified constants on the boundary. More generally, for all t, let's suppose at A we specify some function. You can define the boundary value to be some function of t. This is called a Dirichlet boundary condition. Alternatively, you can describe the normal derivative where we have some region R and a boundary to the region. The normal derivative specifies the derivative given some unit exterior normal to the region. You can define that to take on some functional value. On the boundary of the region. Now, in a one-dimensional problem, like we're about to launch into, the normal derivative will be the derivative with respect to x. And on the boundary of the region, it'll be one of the endpoints of the interval in question. So we'll evaluate x at the endpoint, and we can specify that to be some function. That's called a Neumann boundary condition. So the Neumann boundary condition defines the behavior of the normal derivative of the function evaluated around the boundary, whereas the Dirichlet condition just describes the value of the function, not its derivative, on the boundary. It's possible to use a combination of both Dirichlet and Neumann conditions in a single boundary condition by taking a linear combination. Those are called Robin conditions. For now, we're going to just constrain ourselves to a simple heat equation with insulated ends and some arbitrary initial data. We'll make the assumption that U is separable. Now, there might be some little additions to this for different boundary data, but for now it's good enough to assume that the function U can be separated as t times x. That's not true in general for solutions to the heat equation, but we'll kind of show how to deal with those situations as well. Now, plugging this into the heat equation, we get T dot x equals C T x prime prime. Dividing by Tx on both sides, the x's go away here, the t's go away here. We have T dot divided by T is C times x prime prime divided by x. Now, what do we do next? I like to put the C over on this side. Just as before, both sides must equal a constant since they are functions of different variables. By trichotomy again, lambda can be positive, negative, or 0, and we need to look at the implications of each of those possibilities. Let's assume to start that lambda is 0. If lambda is 0, then x has to be of the form ax plus b for some constants a and b. But to satisfy the boundary data, x at 0 will have to be 0, and that implies that b is 0. Now that b is 0, we look at the other boundary condition. L is not 0. That implies a is 0. If a and b are both 0, x is identically 0, and that implies that u is identically 0. The trivial solution to the heat equation. Well, it may not satisfy our initial data, and so not good enough. Let's see what happens when lambda is positive. You can probably tell right away that since c is positive, and if lambda is positive, then t will have to grow exponentially, which is physically untenable. But we can analyze this in a different way. If lambda is positive, x prime prime minus lambda x equals 0. That implies x must be of the form e to the square root of lambda x plus c2 e to the square root of lambda minus x. It follows then from the data, plugging in x equals 0, that c1 plus c2 must equal 0, so that c2 is minus c1. The other initial condition will then imply c1 e to the root lambda times L minus c1 e to the root lambda times minus L equals 0. If c1 is not 0, you have a problem. we either have C1 is 0 or e to the root lambda L equals e to the minus root lambda L. If we divide this off, we'll get e to the 2 root lambda L equals 1. And that only happens if L is 0. Well, L is not 0, and so this is impossible unless C1 is 0. And if C1 is 0, then C2 is 0, and that implies U is identically 0 again. So again, the trivial solution will throw that out, and we must deduce then the only realistic possibility is lambda is less than 0. If lambda is less than 0, we'll set it equal to negative m squared. You can see then, right off, x prime prime plus m squared x equals 0, which has the solution x equals c1 cosine mx plus c2 sine mx. To satisfy the first initial condition, x evaluated at 0 has to be 0. That drops this term, cosine of 0 is 1. We get c1 must be 0. This term has to go away. The other possibility is x at L must also be 0. The only way that can happen is if ml is an element of n pi such that n is an element of the set of integers. So ml must equal n pi for some n. We'll write m must be n pi over L, where n is an element of the set of integers. This is just what happened with respect to the wave equation. Now, what happens with the other side? We'll have 1 over c t dot over t equals minus m squared, which means then that t is some constant times e to the minus m squared c t, which will be some constant times e to the minus n pi over L quantity squared c t. That gives us our solution. We can combine the two constants as a single constant, which I'll denote as Cn, e to the minus n pi over L quantity squared c t times the sine of n pi over L x. You can see that we have a family of different solutions for different values of n. We can add those up and find a more general solution. So more generally, we'll have the sum. We may as well start n equals 1. Cn e to the minus n pi over L quantity squared ct sine n pi over L x. A more general solution. The question now becomes, how do we choose the values of Cn so that the initial condition will be satisfied? Remember that u at time 0 is specified to be some function u0, where u0 would have a power series representation. Since at t equals 0, we end up with only signs, we'll assume it has some form as a sine series, but Remember, these always look like the sum, as n goes from 1 to infinity, of the inner product of u naught with the appropriate sine function over the inner product of the sine function with itself, this in both of those spots, times that sine function. Using the odd extension of u naught, it makes sense that we could use these odd functions to reconstruct this function. You'll recall from our previous analysis that the inner product of s with s is L over 2, so we'll end up with 2 over L times the sum, as n goes from 1 to infinity, of the integral from 0 to L of u naught of x sine of n pi over L x dx. We should perhaps use a different variable here, s, 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 and then multiply those constants times the sine of n pi over L x. If the initial data has these as coefficients, then the CNs must be 2 over L times these integrals. So in other words, equating coefficients, which you may do for Fourier series, we see that Cn is 2 over L, the integral from 0 to L of the initial data, u naught of x, times the sine function n pi over Lx dx. This will give you these constants right here, so the initial data will be satisfied. As a quick example, let's suppose that we're dealing with the heat equation with the endpoints equal to 0 and the initial data held to be some constant u naught. This is the function u naught that we need to pick apart to find our coefficients. The coefficients Cn are going to be 2 over L, the integral from 0 to L of the constant u naught, times the sine of n pi over Lx. We have then 2 u naught over L. Well, what's the integral from 0 to L? We'll have minus, when we take the integral, we have to divide L over n pi. We'll have a cosine n pi over Lx, and we're evaluating from 0 to L. You can see these L's are going to go. We'll have this minus 2 over n pi, factoring the minus 1 over n pi out. When we plug in L, we'll have the L's cancel. Cosine of n pi is negative 1 to the n. And when we plug in 0, we'll have 1. We can push this negative through and rewrite this as 2 over n pi times 1 minus negative 1 to the n. If our coefficients are 2 u naught over n pi times 1 minus negative 1 to the n, then our solution u will look like the sum, as n goes from 1 to infinity, of 2 u naught over n pi, 1 minus negative 1 to the n, those are the constants, e to the minus n pi over L squared ct times the sine of n pi over L x. Let's define U naught to be 7,000. Well, we can just say 1. And we'll define our function U, mapping, mapping t and x onto 2 times U naught divided by pi times the sum, and we had 1 minus -1 to the power of n divided by n times the exponential function minus, we had n times pi divided by L. Let's define L to be 1 squared times C. Let's suppose that C is also 1 times T times the sine of n times pi divided by L times x. Let's have n go from 0 to 10 to begin with. And we'll animate this. We're going to have U of t comma x. X equals 0 to 1. And t goes from 0 to 1. Let's start off to begin with and just see what happens. Color is black. Let's use 50 frames. And of course, I left off. It's giving me a division by 0 because I started at 0. There we are. There's our plot. It with n equals 10, it doesn't look very good. You can see what happens as time progresses. As t goes to 1, this thing shrinks down to 0. It starts off more or less constant. And because the ends of the bar are held at 0, the temperature quickly shrinks to 0 across the entire thing. Let me stop this and increase the number of frames. And let's also increase the resolution of this thing. You can see the plot is much better by increasing the number of terms. We'll see if the animation is better by increasing the number of frames. This looks very much like Lord Kelvin's analysis that he used for estimating the age of the Earth. He had the Earth start off at some nice uniform temperature, at the temperature of molten lava, maybe 7,000 degrees, and then slowly over time, with the boundary condition of 0 degrees on the surface of the Earth, he had the Earth cool, and you could determine the age of the Earth based upon the temperature profile, especially near the surface. His analysis over the course of a very long period of time looks more like this, however. Let's see if we can make this run a little better. Yeah, according to his analysis, the interior of the Earth is still very, very warm. And it stays that warm for a long period of time. It's the rate at which temperature increases as you go into the interior of the Earth that he uses to measure how old the Earth is. You can see this slope gets shallower and shallower as the Earth ages. In this case, we're looking at just a simple one-dimensional bar, but it's very similar for the Earth itself. I'd next like to look at the initial boundary value problem for the heat equation when the endpoints are not held at 0, but at something else. At the left-hand endpoint at 0, we have some left temperature. At the right-hand endpoint, when x is equal to L, we have some right temperature. And it turns out the solution to the problem with 0 boundary data will come up in the solution to this problem. First, note that if as t goes to infinity, the solution goes to some steady state, then ut will be 0 on the steady state. U infinity will be a function of x, which implies it will satisfy 0 equals c u infinity x x. That implies then that the infinite state, the steady state at infinity, as a function of x, will be of the form mx plus b for some constants m and b. To satisfy the boundary data, ul must be what happens when you plug in 0, so that the constant b is the left constant state. U right is what happens when you plug in L. B is now UL. That implies then that M is the difference between the right and the left states divided by the length of the rod. We have then that the steady state at infinity is going to be U right minus U left divided by the length of the rod times x plus U left. You can see if you plug in 0, you get the state at the left. If you plug in L, these will cancel and you'll get the state at the right. Now, it turns out if U is of the form W plus U infinity, then this will solve the differential equation precisely when W is a solution to the heat equation. You can see that because if you plug it in, if you take the derivative with respect to t, what you'll get is Wt plus 0. U infinity does not depend upon t. But Wt does solve this differential equation, so you get c times W xx. But remember that the second order derivative of U infinity with respect to x is also 0. And hence, we get c times U xx. Anytime you take an arbitrary solution with the eventual steady state solution and add them together, you get a solution. The only question that remains is, we know that U infinity satisfies these boundary conditions. It turns out W then had better satisfy 0 boundary conditions. If this is going to be 0 and this is going to be UL and UR, then U will satisfy these two boundary conditions. There's only one more issue to address, and that is, what initial data does W have to satisfy? It's easy to figure that one out too. If U naught has to be what you get when you plug in 0 for the solution, then if U is W plus U infinity, what you'll have is W evaluated at 0x plus U infinity of x. It only depends upon x. So when you plug in 0 there, that's what you get. It implies then that the initial data for W must be the original initial data minus the steady state solution. there. To solve the general initial boundary value problem, all you have to do is, first of all, construct the steady state solution. You modify the initial data by subtracting the steady state solution, and then you find another solution that satisfies the differential equation with zero boundary data. That gives you the entire solution just by adding them together. This allows you to model what happens, say, with a reflux column at a refinery, where you have gases being input at a specified temperature at the bottom. They float up the column and they're cooled as they go up. They leave at a particular temperature at the top. So you're holding the input temperature and the output temperature at some constants. And you can see what the evolution of the temperature will be in the reflux column as time goes by, as it tends towards that steady state solution, which will be a straight line. To make this clear, we let W solve the differential equation with zero boundary data, but the arbitrary initial data modified by subtracting u infinity. The solution then will be W plus the steady state solution that we found earlier. Notice that W is transient. It has this factor e to the minus pi n over L quantity squared Ct, which goes to 0 as t goes to infinity. So this part will vanish as time goes by, leaving only the steady state temperature as t goes to infinity. Let's look at an example of a bar with insulated ends. In this case, we'll have Neumann data and the initial data is whatever we want. In this case, the separability requirement is that we have some constant plus xt. The solution will have some form like this. It's a little bit different. We're not assuming a direct product, but a constant plus a product in this case. If that's the case, what do x and t have to satisfy? We'll plug that in here. xt dot is c times x prime prime t. We'll divide by xt. Again, x's go away on one side. We'll put the c over here. The t's go away, and we'll have a constant equal to each side once again, as per usual. Once again, we have to deal with trichotomy. Lambda equals 0 implies, again, the second order derivative of x is 0, which means x is of the form mx plus b. And we need to satisfy the boundary conditions. So if u is a naught plus xt, du dx will be x prime times t. If that's equal to 0, we can forget about the t. X prime will have to be 0. So 0 will have to be x prime. Well, that gives us x is a constant. That seems like a dubious prospect for finding a solution. Nonetheless, this will also satisfy the boundary condition on the right-hand side as well, the insulating condition on both left and right, because the derivative at the right will also be 0. So if x is a constant, then u is going to be a naught plus bt. It'll be a function of t alone. Seems like a very dubious way to solve for arbitrary initial data. But also, we must deal with the fact that 1 over c, t dot over t, is equal to 0, which means t is constant. But if t is constant, then u is identically constant. And, well, that just means we have a very simple situation here. U identically constant. Yeah, that's going to solve the heat equation every time. But it won't solve necessarily the initial data. So let's look at the other cases besides lambda equals 0. If we assume that lambda is greater than 0, then 1 over c t dot over t equals, let's suppose lambda is positive m squared. That gives you t equals e to the m squared ct, which goes to infinity as t goes to infinity. So we have an object that blows up, temperature that blows up as time goes on, which we can throw out for physical reasons. But we can do a more thorough analysis of this. If we have x prime prime over x equals m squared, we can move the x over, and we have a function whose second order derivative is a constant squared times itself. It's easy to check that solutions are c1, hyperbolic cosine of mx, plus c2, hyperbolic sine of mx. Now, the boundary conditions were these Neumann conditions. We need to find x prime and set that equal to 0. X prime will be m c1 times the sinh of mx plus m c2 times the cosh of mx. Evaluating at 0, notice that the hyperbolic sine of 0 is 0 and the hyperbolic cosine of 0 is 1. So we get mc2. Well, m is not 0 by design, so that implies that c2 is 0. So this part of the solution is out. Let's see how we get the other boundary condition to hold. At the other boundary condition, we have 0 is this x prime evaluated at L. Well, m is not 0. c1 might be 0. The only way hyperbolic sine is 0 is if the argument is 0, which means that m times L is 0. Well, neither m nor L is 0, and so that implies that c1 is 0, but that just gives you x is identically 0, and hence u is u naught, which is identically constant again. Well, there's only one more option by trichotomy. That better be the right one. And when you think about heat problems, you kind of expect that constant lambda to be negative. So let's have lambda less than 0. We'll have x prime prime over x equals minus m squared. We'll assume that lambda is minus m squared. In this case, x will be of the form c1 cosine of mx plus c2 sine of mx. And that implies then that x prime is negative m c1 sine of mx plus m c2 cosine of mx. Now we need to satisfy those Neumann boundary conditions. So 0 is going to be x prime of 0, and if you plug in 0, this goes away. We end up with mc2 because cosine of 0 is 1. M is not 0. So that implies C2 is 0. That term must go away. We also have to get 0 at L. And so plugging in L, we have minus m C1, the sign of mL. Well, if m is not 0 and C1 is not 0, that implies that mL equals n pi, where n is an element of the set of integers. Where have we seen that before? So m will be n pi over L once again, but we're going to have cosines this time, multiplied by that function that solves the differential equation on t. So we'll record here that we can absorb the constant into the function for t. We'll just have the cosine of n pi over Lx. Now we have 1 over c t dot over t equals minus m squared. We'll move the c over and the t over, and we'll see immediately that we get a constant, which we'll put a subscript on, e to the minus m squared c t. That then gives us u is some a naught, a constant, plus cn e to the minus m squared ct times the cosine of n pi over Lx. And this actually gives us a family of solutions that we can sum. Since the sum of constants yields a constant, we can see that u is going to be some u naught plus the sum as n goes from, I suppose we could start at 0, but that would just give us more of a constant. So 1 to infinity of the cn's e to the minus n pi over L quantity squared ct cosine of n pi over Lx. The only question that remains is how do you get these cn's from the initial data? Seems like we've solved that problem before. Let's complete this. You can see then that u at 0 will be u naught plus the sum as n goes from 1 to infinity of cn cosine n pi over Lx. Remember, if our Fourier basis is 1 cosine n pi over Lx sine n pi over Lx, n goes from 1 to infinity, we have to account for this 1. So the coefficient, this u naught here, or a naught, I guess we called it, a naught should be the inner product of 1 with the initial data over the inner product of 1 with 1 times 1. That should give you that first term. The inner product of 1 with 1, since we're integrating from 0 to L, gives you L. So we're going to have L down here, not L divided by 2. So have 1 over L, the integral from 0 to L of u naught of x dx. That gives you that constant a naught. Notice that this is the average of the initial temperature distribution. Also, Cn should be the inner product of the initial data with our cosines. And the inner product of the cosine with itself was L over 2. So we should have 2 over L, the integral from 0 to L, u naught of x, cosine, n pi over Lx dx. These constants, along with a naught, which was the average of the initial data, gives us the complete solution to this Neumann problem, the insulated end bar problem. We turn next to the heat equation applied to a bar with one radiating end. We'll assume the left boundary value is identically 0. But on the right-hand side, we'll have minus k times u. So the rate at which we have heat being thrown across the boundary is proportional to the amount of heat there at the boundary. We add, of course, initial data. We'll try the separability condition again, which leads, of course, to 1 over c t dot over t equals x prime prime over x, which is lambda. We'll consider the three cases that result from trichotomy again. If lambda is 0, then x is mx plus b, but to satisfy the left boundary condition, x at 0 will have to be 0, and that implies that b is 0. So x will be m times x. Now we have to satisfy the right boundary condition. If we take the derivative, we'll have to have x prime equals minus kx when evaluated at x equals L. X prime is m. X evaluated at L will be m times L. The only way that can happen is if either m is 0 or if m has a very special value. K is related to the rate of heat flux across the boundary and L is just the length of the rod. It seems implausible that you could get this to be satisfied for arbitrary values of K and L. It seems much more plausible that m is 0, in which case u is identically 0, which solves the problem except for the initial data. Well, let's throw this case out then. We'll look at the lambda positive case. If lambda is positive, we can set lambda equals m squared. In this case, x will be c1 hyperbolic cosine of mx plus c2 hyperbolic sine of mx. To satisfy the left boundary condition, 0 equals x of 0, but when we plug in 0, hyperbolic sine of 0 is 0, hyperbolic cosine of 0 is 1, we'll have c1 is 0, which means this part goes away. X prime then will be m times c2 times the hyperbolic cosine of mx. If we evaluate that on L, we get m c2 cosh of ml equals minus k, and then c2 sinh of ml. You can see that either c2 is 0, or we'll have some complicated relation involving m and l. The complicated relationship will be minus m over k equals the hyperbolic tangent of ml. So if we assume c2 is not 0, we'll divide the negative k over, divide the cosh over. The problem with this is that we have a value that is negative on the left. Hyperbolic tangent is only negative when its argument is negative, but m and l are positive, so that can't happen. That implies then that c2 is 0, and that implies then that u is identically 0 once again. So we'll throw this case out as well. So lambda is negative. Lambda will be minus m squared. That gives us x prime prime over x equals minus m squared, and once again x is going to be c1 cosine of mx plus c2 sine of mx. Again, to satisfy the initial data, sine of 0, 0, we get C1. C1 must be 0. This first term must cancel out. To satisfy the next initial condition, x prime is going to be mc2 cosine of mx. Evaluating that at L, we get mc2 cosine of ml equals minus k, and then c2 sine of ml. So either c2 is 0, or again, we'll have some complicated relationship involving the tangent this time of ml. The tangent of ml will be negative m over k. Notice that tangent looks like this, repeating itself over and over, and here we have a line with negative slope going through the origin. It should strike the tangent curve a large number of times, including at 0. Tangent of 0, 0, you'll get 0. So we're going to have these values, m0, m1, m2, and so on, an infinite sequence of values from which it looks like we can construct solutions. However, their analytic representation is a bit confusing and difficult to find, though we can numerically solve for these once we know what k is. We'll use these values to construct a solution just as we did with the roots of the sine function in pi before. We'll have then a selection of values, m sub k, as k goes from 1 to infinity, that solve this equation. We'll use these to construct our solution. We'll have then u is the sum, as n goes from 1 to infinity, of constants cn e to the minus mn squared ct times the sine of mnx. Our Fourier basis this time is the sine of these mnx's we'll use these to pick apart the initial data to figure out the coefficients. At t equals 0, we'll just have cn times the sines. That means then that cn must be the inner product of the initial data with a basis element divided by the inner product of a basis element with itself. The inner products will be integrals from 0 to L, and without further specifying what the values of the mn are, which we can calculate numerically if we know the constant k, then we really can't proceed much further than this in this analysis, other than everything's pretty much done except for plugging in the constants in the problem.